I can see that you are not muted. So perfect.
Okay. Hopefully, if we leave that there.
Oh, then I sent you.
So
Maybe. Thank
yeah,
you.
hopefully.
Okay. Is that good now? Maybe someone from the.
Yeah,
okay, now they
I think that the sound is coming from that. Sorry.
Sure, no worries. So what will happen is that now that I define these two variables x4 and x5, they are not independent of each other. But now if I condition on x3, they are going to be conditionally independent. I just wanted to, with this slide, tell you that conditioning can really affect the dependency. I mean, we should not expect the same phenomena from dependence when we go to conditional dependence. It can change the situation dramatically. And measuring conditional dependence, it has been addressed in the literature, starting from maybe the simplest idea of partial correlation, methods that use entropy-based methods, distance correlation, and then later people realized that actually distance correlation is a special member of the more bigger family of kernel-based methods, and then we have another area using copulas. Most of these works are in the parametric setting, and the focus mostly has been on conditional independence testing. So today, what I want to introduce to you is not really on testing conditional independence, but is to actually how to measure conditional dependence. So let's see what is the problem, how can we address it, what are the difficulties. So let's say I have two random variables, x, y, and z, and we have their joint, let's say, characteristic function or density or whatever you wish. By definition, y is independent of z conditional on x. If I can decompose the conditional density function of y and z given x as the multiplication of their marginal conditional density function. So y given x and z given x. Now, a very natural idea is to, okay, look at the difference of these two functions, whether half y is this f of y and z conditional on x minus the decomposition. If this difference is 0, they are completely independent conditionally. The farther distances, they are far from being conditionally independent. The problem here is that, of course, in reality, we don't have the access to this characteristic function or density function, and estimating it is not easy, especially if we go to a little bit higher dimensions. So what do we do then? The measure that I'm going to define today is called CODEC, standing for Conditional Dependence Coefficient, and just a high-level advertisement, basically. It has a simple expression. It is fully non-parametric. You don't require any tuning parameter. So whether you use it or I use it, we end up exactly the same, having the same result. You don't need to estimate any conditional density or characteristic function, which are difficult tasks. So basically, we are going around this difficult task. And then there's absolutely no assumption on the law, the joint law of these random variables, discrete, continuous, whatever you wish, it can handle. Let's go back a little bit in the history. So there is this paper by Albert Rennie, I think it's 1959 or something like that, where he talks about measuring dependence, just simple dependence, and he requires some criteria for a pleasant measure of dependence. The first property that he says that maybe we should require from any measure of dependence is that maybe it should be bounded, for example, between 0 and 1. The other property is that this ends of our bound, the end of the spectrum, 0 and 1 should have meaning in the sense that the measure is 0 if and only if I have independence, the measure is 1 if and only I have full dependence. And one other property that he required was that he required that this measure would be symmetric in the inputs of y and z. Now, with these requirements of Rennie, I want to introduce our measure. I start with the simple case where there is no conditioning involved because carrying the intuition of the definition is just easier. And then I will go to the conditional case. So for the start, we have y, which is a random variable, one-dimensional. We have z, which is possibly higher dimension, so q-dimensional, and mu, which is the probability law of y. So now I just what I want to answer is to somehow quantify how much y depends on z. With these three ingredients, I define t of y and z as the measure of dependence of how much y depends on z in this shape. So you see, t of y and z is the ratio of two integrals. Each integral is with respect to mu, which is probability law of y. You can basically think of it as CDF of y. And then it's some integration over some variance. I advertise the measure as something that has a simple expression. You may be like, well, you lied to us. It's not very simple. I agree. But let me make it a little bit more colorful to see that actually it is not that complicated and it is simple. So in the colorful version, you can see the similarities and differences between the numerator and denominator. Again, we have a ratio of two integrals over the real numbers. The integration over all the values of t that y can take. So it's with respect to the law of y. In the denominator, I'm taking integral of variance of indicator functions of y being greater than some value. And in the numerator, you see it's basically the same thing with a slight difference. Again, I'm taking variance of a function of this level set of y being greater than t. What is that? Conditioning on z. But why am I doing this? By the way, if you have any questions throughout the talk, feel free to interrupt me. So let's say that the plane that we are projecting on is the sigma algebra of all the randomness that we can create with z and y. And assume that the horizontal axis, this black horizontal axis, is the sigma algebra generated by z. Now, in a very general case, my indicator function of y being greater than t, in the general case, would be something like this red vector, lies in the 2D plane. And what does conditioning mean? Fortunately, conditioning has this very nice geometric interpretation, which is projection. So conditioning on z, the conditional expectation of this level set of y, conditional on z is basically projecting this red vector, y being greater than or equal to t, on the horizontal axis. And I will get this green vector. Now, I have the red vector here, which was the level set, that I'm looking in the denominator. And then I have the green vector, which is the result of the projection. And then note that I'm taking variance of these two entities, basically. But what is variance? Variance is nothing really but the L2 norm of these two vectors. So what I'm in reality doing is that I'm comparing the average length of the green vectors in the numerator compared to the average length of the red vectors. So let's see, what does it do? Imagine that we are in the situation that y is fully a function of z. What does it mean? It means that y lives in the sigma algebra generated by z in the horizontal axis. So conditional expectation, projection doesn't do anything to it. So the red vector is already on the horizontal axis. By projecting it, I do not change it at all. Keep the length. The numerator and denominator will be equal. I get the 1. The very other extreme end of the extreme where y is fully independent of z, this red vector is completely perpendicular. Conditional expectation keeps all of its length. I will end up having a 0 in the numerator. So in the independence case, I will get a 0. Now with this intuition, we can maybe continue seeing what are the properties. Again, because conditioning does not increase the variance, just by definition, we can simply see that the first property that Rennie asked for is satisfied by this definition. Our measure is bounded between 0 and 1, with 0 being happening when we have full independence, and 1 if and only if we have full dependence, meaning that y is a function of z. a nice property that we can maybe ask for a measure of dependence is that if I add some extra stuff, let's say I amend this W to my Z, the measure of dependence should not decrease. In the worst case scenario, it has nothing to do with Y and it wouldn't change, but I would expect to have it at least increasing. This property is saying that we have invariance under one-to-one transformation. It's something that it is important to have. Let's say I'm changing the unit of measurement from centimeter to inches, for example. The measure of dependence should not rely on this sort of transformation. So it will capture that. Our work, we were working on this topic in say, around 2020, and we realized that this idea actually was published already in 2013 by the work of Delta, Seberg, and Stormenov, where they addressed the problem from the copula perspective. And what they did actually, they started by defining an estimator and showing that the estimator has a limit, and the limit was exactly the measure that we defined. But the estimator is using copulas, and it's a totally different story. Now, the question is that what I told you, let's look at the measure again. So here I have these integrals and variance and conditional expectations, and which means that you may ask, okay, how do you estimate this thing? Because I said that we don't have access to the density function or characteristic functions or things of that sort. So without knowing any of this and claiming that I don't need to estimate any of that, how am I going to estimate this thing? And let me introduce you the estimator now. So for the estimation, you need a sample of size n for i.i.d observation of these di's and yi's. The second ingredient that you need is the rank of each observation y. So for each observation y, basically you see, if you sort your yi's, where is this observation standing? The next thing that you need is to, for each zi, look among all the other zij's, figure out what is the nearest neighbor of zi among all the other zij's, and call that zn. So with the rankings and these nearest neighbors, we define the estimator in this shape. So the estimator is a ratio of two sums over the elements of the sample. And let's take a close look. What are the ingredients of the numerator and denominator? I see the ranks are appearing. So rank of each y is here. And the other thing is the numerator. I see the rank of r and I, meaning that the index of the nearest neighbors of the I is appearing, but really nothing else. So what's the advantage? The advantage is that finding the ranks is super easy. Just sort, and any sorting algorithm that is proper will do the job in n log n time. And finding nearest neighbor is also not that hard. There are very efficient algorithms that do the job in n log n time. So the estimation is as efficient as we can ask for. Now, you may ask that, okay, what is the intuition behind this estimator? Because it's just by looking at it, it really doesn't spark what is the immediate relationship between the estimator and the definition of the measure with all those variances and integrations. So now I try to give you some intuition. So this was our original measure. And looking at the denominator, we can guess that estimating the denominator is not that hard. That's the easy part. Why? Because variance of this indicator function is a Bernoulli random variable. It's easy, we know it. And then it's just a matter of estimating the CDF function of y, which is kind of equivalent of finding the ranks. The hard part is the numerator, where we have this conditioning. Now let's focus on that a little bit more. So what I can do is that with the law of total variance, I can write what I want to estimate is variance of the conditional expectation of the level sets as the variance of the level set minus the expectation of the conditional variance. So variance of the level set, we said that it's easy. So now I focus on estimating the expectation of these conditional variance. So the hardness is clear. I don't have access to this conditional density. If I had, the problem was already solved. But we don't have it. But let's say that we are lucky and we are able to, let's say, generate y and y prime, i.i.d, given z. If I could do that, then I with a little bit of playing, I could write this conditional variance as half of conditional expectation of the difference between these level sets of y and y prime. Right? This is just because y and y prime are i.i.d conditional. Then note that this quantity here is either 0 or 1. When is it 1? It's 1 whenever t is exactly between y and y prime, and it's 0 otherwise, right? So basically, it's asking for all the values that are between y and y prime. Now, unfortunately, we don't have access to this y and y prime in reality because I only have one sample. And if z is continuous, there's very unlikely to see multiple observations with the same z. So what do? Now that's the part that we start basically cheating. I don't have y and y prime i.i.d, but let's say the nearest neighbor of zi, z and I, is close enough to zi such that I can pretend that the y and I that belongs to z and I has almost the same conditional distribution given zi. So if my z and I is close enough to zi, I can exchange assume that the two y's are exchangeable, and this y and I is playing the role of the y prime that I needed. Doing that and looking at the variant, the definition of the variance, we can see that what we were looking for is basically counting how many other yj's are going to be between these two yi and yi. And that would basically show up in the difference between the rank of yi and the rank of yni. So ri and rni in the definition of the estimate. Any questions?
Just a quick question. I would mention that 0 is perfect independence.
Yes.
1 is perfect dependent.
Exactly.
So somewhere in the middle is like a random function.
That's a very good question, actually. Let's go back to the measure. So when you look at the measure, you see I have taken integral of all the randomness involved, which is something important because the measure should not be a random object. So then the measure itself is fully deterministic. Between 0 and 1, the meaning is that you can think of it as correlation. If we have linear correlation equal to half, what does it mean? It doesn't carry the exact meaning, but it means that there is an amount of dependence, but it's not what you cannot write your y as a function of z.
So like the single algebra is not like a strict subset of.
Exactly. Yeah. Yeah, exactly. That's a good point. Yeah.
So why don't you just like add the two versions?
Yeah, that's a very good point. So as I said, Remy asked for a symmetric measure, right? But one solution, as you say, is just look at how much y depends on z, how much z depends on y, take average or take maximum, whatever you want, and give that as a symmetric measure. I want to say, actually, maybe in that part, I disagree with respect to Remy, because I think we should not think of dependence as something that is symmetric. I can give you an example, an easy example. So let's say that y is z squared, where z is normal 0, 1. If I give you the value of z, y is fully deterministic. But if I give you the value of y, you can only determine z up to a sign, which means that, there is some asymmetry. And I'm hoping that maybe this gives some direction to how we can address this asymmetry and take advantage of it. Okay. How much time do we have? Oh. So now that we have some intuition from the simple unconditional case, let's go to the conditional case. Now what I want to do is to see how much y depends on z given this random vector x, which can be three-dimensional. So everything goes the same, except I have one more vector x that I'm conditioning on. And here is my measure, how much y depends on z given x. Again, let me show you the more colorful version. It's easier to look at. So the similarity with the simple case is that, again, I have a ratio of two integrals with respect to the law of y. I have everything is almost the same, with one subtle difference that I have one extra level of conditioning on x. And where does that come from? Remember that when we want to measure the dependence of y on z given x, they may have some shared information from x, which I'm not interested in. So by doing this conditioning on x, I'm getting rid of that part of dependence that is coming through x, and it helps me to measure the remainder of their dependence that is full just between them, and it's not coming through x. Again, with the properties of conditioning, we can see that we have this boundedness property with the two ends having the same meaning, in the sense that my measure this time is equal to 0 if and only if I have conditional independence, and it is equal to 1 if and only if z is a function of, y is a function of z given x. Again, I have invariance under one-to-one transformations. And yeah, as you mentioned, our measure is non-random, so it's a deterministic. So everything, all the randomness has been killed. For the estimation, you can guess. So again, we need this time a sample of all this y, x, and z. This time, I need two searches for finding nearest neighbor. One search is to look at, find the nearest neighbors of each xi. So for each xi, remember x is the variable that I'm conditioning on. I find x and I. And then the second time, for each pair of zi and xi, I'm finding mi, which is the index of its nearest neighbors among all the other pairs. Again, I'm required to find the ranks, which is sorting of y. And my estimator will be now this shape. Again, you see that the only things that are appearing is the ranks with respect to the nearest neighbors of pairs, and ranks with respect to the nearest neighbors of x's. The first thing that you expect from any estimator is consistency. And so that's what we could show, that almost surely as the sample size grows to infinity, we have convergence of our estimator to true measure. Not that there is no assumption here about the distribution or anything, which then it's at the cost of having almost sure convergence. It doesn't tell you anything more. So it might be that your convergence is super fast, or in some examples, it might be super slow. But if you want to say something more, we need to make some assumptions. So the first assumption here is that the conditional probability function of y given the variables should follow some sort of a Lipschitz assumption. And the second assumption is basically controlling the size of the support of x and z, that they are not crazy heavy things. If these two assumptions are satisfied, then you can see the rate of convergence of Tn to T depends on the dimension of x and dimension of z in this shape. And as you can see, if P and Q are large, this convergence can be quite slow. This assumption is basically trying to say something about, or we require this assumption because in the part that we are cheating and pretending that I can exchange the y and I as the y prime, if the distribution is very volatile, I cannot make such an assumption. So this is taking care of that part, and this part is taking care of the distance between the nearest neighbors. So if the domain of the variable is super crazy big, I cannot have a control whether the zi and zni are close to each other. So this is for that part. But let me show you an example. This is a tough example, I would say. I have x1 and x2 that are uniform and i.i.d on 0, 1. Then I define y as the sum of x1 and x2 mod 1. What do I mean by that? Add the x1 and x2 and take the non-integer part of it. So for example, I have 0.3 and 0.8, 1.1, y would be 0.1. Now, this example, I would call it a tough example. Why? Because y is individually independent of x1 and x2, although it's a function of both of them. But then if you condition in one of them, it would be, of course, the full function of the other one. So marginally, it's independent of each of them, but conditionally, it's a full function of the other one. And I want to see whether our estimator or our measure can capture this situation. So what I did was that I generated 1,000 independent samples of size 1,000, and I calculated the Tn of y and x2, how much y depends on x2, and what this time conditional on x1. So here you can see this histogram is centered at 0, which is really capturing the independence of y and x2, and the red histogram is very close to 1, which is capturing the case that we have full dependence conditional on the other one. Now, an immediate application of any measure of dependence would be in variable selection. And we also tried it. And so we came up with an algorithm that's called FOCI. So this algorithm is a model-free forward stepwise algorithm. We have a random variable y, and it's our response variable. Then I have a vector of features, and the question I want to answer is that without any assumption on the relationship of y and these features, is there a way such that I can select a subset of xi to xp that explains the y the best? What do I mean by explaining the y the best? I mean it has full dependence. Sorry, not full dependence, it has maximum dependence on that subset. So you probably already have known or guessed what am I going to do. The first, before the start, I have a set I call it S hat, which is an empty set. I'm going to put selected features one by one into this set. So in the first round, I'm going to do a screening. For each feature xi, I'm going to see how much y depends on that xi, pick the one that takes the maximum value, let's say that one is j1, put it into my set S hat. Now that I've already picked the one that maximizes pairwise dependence, I'm going to conditional on that one. So conditional on the variable that I've already picked. Another round of the screening, how much y depends on any of the remaining ones, pick the one that maximizes it, put it into my set S hat. Third step the same. So now I have picked already two, a condition on the first two selected, pick the one that maximizes the dependence conditional on the already selected ones. I continue like this. Okay, when do I stop? Like, am I gonna continue like this? Or what's the goal? Fortunately, the algorithms comes with a natural automatic stopping rule. So let's say we have already picked k variables xj1 to xjk. Conditional on them, I'm doing another round of screening. I observe that none of these measurements are positive. That's a sign that I should stop. Why? Intuitively, it's saying that given the set that you have already picked, none of the other variables is going to contribute to the structure, meaning that not all the other remaining variables are kind of conditionally independent. I say that in a quotation mark.
T is positive.
Sorry?
I thought T is positive.
That's again a very good point. T is positive, but it is our estimator. So the estimator could actually take negative values, which you can interpret them as 0 somehow, but it's in a very non-rigorous way. So if I observe that the dependency of the remaining one is not positive, then the algorithm tells me that, okay, stop, and just report the selected set. Now, let me show you an example. So here, I have a feature vector of dimension 1500. Each of the x's are i.i.d, normal standard. My sample size is 1000, and the dependency between y and xi is in this fashion. So y is x1 times x2 plus sign of x1 times x3. What I did was that I let the algorithm run and stop by its stopping loop. So first an algorithm picked 1, 2, and 3. All the 3 signal variables did not pick anything wrong and stopped. Now, all the other selection methods, forward, stepwise, lasso, dancing, they either didn't select or they selected a bunch of variables that were not signal variables. They were not successful at all. And what I want to say is that building such an example is actually not hard. It was very easy to build this example. Why? Because all these other methods, they rely on this linearity assumption. For example, lasso, it does a great job as long as the Taylor expansion of your function has a good linear part in it. And in that case, it is very successful. But as soon as you have some terms such as these functions, like x1, x2, these interaction terms, methods that rely on linearity, they fail. And this is the success story of this algorithm, that because we do not have any assumption on the functional form, we don't fall into these situations. Yeah, but if you can add those and put the same thing we had.
So you try.
Yeah. Now, what can we say about the properties of FOCI? So for this, I need a little bit of definitions. Let's say that I have a set S, which is a subset of the indices of my feature space. I call it a sufficient set if Y and all the other variables that are not, their index is not in S, are conditionally independent given this set. This is also known as Markov blanket. Then I define this Q function as in this shape, which is basically the numerator of our measure. And then I have this delta, which is going to be the largest number, such that for any insufficient set S, if I add any index j to my insufficient set, the amount of dependency would increase at least by delta. So with these definitions, then I can tell you that as long as delta is positive, and as long as we have those assumptions for the rate of convergence, then an algorithm FOCI with high probability would pick a sufficient set. So the output of FOCI would be a Markov blanket. And note that here, I'm just saying a Markov blanket. I'm not claiming anything about the size of it. For example, I think one interesting question would be to see whether we can actually get the smallest Markov blanket or something of that sort. But for now, unfortunately, we don't know it. I have an example, sorry. Maybe I skip the example for the variable selection and I'll tell you what has been done. So this is a work of Shi, Droton, and Han, and they showed that under independence, we can show that the estimator is asymptotically normal, and they figured out the asymptotic variance. And then later, Lin and Han, they showed that the estimator around its mean is also asymptotically normal. Note that this is important because studying the bias of this estimator is not an easy task. So that's something that we have been working on. There have been other works showing that the original estimator is not powerful against many alternatives. So there has been works to increase the power. For example, in the work of Lin and Han, they showed that if you actually, instead of using just one nearest neighbor, use m nearest neighbor, you will have the same properties plus boosting the power of the estimator. And with this, I would say thank you very much. There is an R package with the name of FOCI, and I'd be happy if you ever use it. Let me know how it is, and yeah, if you have any question, I'd be happy to answer.
Thank you, Mona. Really nice talk. We have time for questions. Yes.
So in the stepwise selection, you stopped when the method gave a non-positive. Is there a natural threshold such that you can say, even just a theoretical metric, that there is negligible conditional dependence or there is essentially conditional independence? Is there such a natural threshold there?
I am not sure if I quite understand. So for being for me, then the stopping rule, this stopping rule is natural in the sense that imagine you actually have access to the true t, not the tn.
Sure.
If you get to the point that t is not positive, it's 0, it means that conditional on the ones that you have already selected, you are independent of everything else. So adding more would not give you. Now you're saying that if I define a margin, you are saying that if I define a margin, then I would not gain much.
Well, no, I'm asking more in the kind of idea that if I were to use this in practice, I was using this measure in practice, I probably wouldn't expect to see 0 and 1, even with theoretical.
I see.
So is there a natural epsilon around those where you can say, yes, we consider this to be essentially,
Okay, I see now you're doing. So yes, so now I guess in this setting, unfortunately, with the nearest neighbor, with the one nearest neighbor, we still don't really have any control over the bias. So I cannot tell you that what should be the epsilon be. But we have a work that actually just got finished 2 days ago that we use a different approach for the estimation, and there we can control the bias, and then we can actually say more. So in that context, with this version, unfortunately, no, but with a little bit of more complex estimator, we can say something about the epsilon.
Just following on from that, I mean, if you were imagining creating a hypothesis test about this, Harlow type test, you might simulate data that are gone in that direction to report that testing.
Testing that we still, because the bias is really an issue. So because we don't have the bias, we cannot say much. You really need to just take the bias and then do something in that. But for not the conditioning, but without the condition, actually. This might be marginally correct, but there has been some work showing that m out of n bootstrap gives you consistency of the testing. So I would say that might be a way to address the problem. Yeah.
Kaiwan, we see your hand, but we cannot hear you, unfortunately. So if you don't mind typing
Yeah, I can turn this up.
Yes.
We should be able to hear you if you speak now.
Yes. So perhaps we can hear now.
Oh, can you hear me now?
Yes, we can hear.
Okay, that's good. Sorry, yeah, it's easier to talk than to. Oh yeah, thank you very much for the talk. I did understand something, and then I have 2 questions. If you don't mind, it will be quick. First, in the conditional case, when you have this measure, how do you get rid of the randomness of x? Is it? I assume it's a deterministic thing, right? So, but it's conditioning on capital X. Do you do it for all?
Yeah. I see what you mean. So actually, let me go back to the definition of the measure.
Yeah.
Yeah. So you see, I have a conditional variance of X, and the outer expectation, which is in blue, it's doing that. It's
Okay, so you
getting-
take the
yeah,
average of all
Exactly.
such X's.
Yeah, exactly.
I see. Because I was wondering if because there is this context-specific independence, right? When you condition on something specific. I wonder if you don't do that E and just let X be equal to some context, some small X.
I see, yeah.
Whether that would be a measure for context-specific conditional independence. I assume it must be.
Oh, yeah, yeah, I think so. Yeah, I guess that would, yeah, I would say probably yes, but then my other, if X is a single value, then I would say maybe it's basically independence, and you can forget about conditioning. But I'm not sure. Maybe I need to think a little bit more about it.
Sure. And one other question I had, so there are some properties in graphical models that are interesting properties of conditional independence, and like semi-graphoids, and there are some other properties that are important, but they're not always satisfied by probability distributions. So I wonder whether such a representation could help with understanding those conditions, things like, even simple things like composition, where A is independent of B given C and A independent of D given C implies A is independent of B and D given C, or things like that.
I see. I actually haven't put any thought into that, so I'd be happy to talk offline.
Okay, yeah. I mean, it might help this type of.
Yeah, definitely.
Because these are exact, right? Yeah, if and only if is exact in
exactly. Yeah.
Okay. Yeah. Thank you very much.
Of course.
Thank you, Kaivan. Yes, go ahead.
Yeah, I have one question actually along the lines of Kaivan was saying. My question is something think of that dependence condition. I see there might be dependence on some values of X, but it's not. Anyhow, that was an aside. My question was, I'm trying to put this in my head. What is T for that example? So the Y is equal to S squared. So one way is 0, is 1.
Oh, the other way.
What's the other way?
I don't know. The other way is probably 0.9. Yeah, I don't know. I don't know the value.
I'm just trying to get a sense of the numbers. I guess there's two sources, right? One is the marginal distribution.
What I can tell you is that, okay, this question actually has been asked before, that linear correlation has a very intuitive meaning. What does it mean that it's 0.7? With this measure, I cannot tell you what does 0.7 mean, because simply you can have two different scenarios with getting 0.7, and the functional dependence is totally different. But for example, if you want to compare it to the Gaussian case, if this is too small, I assume. So if we have linear correlation, let's say I want to have Y as alpha X, where alpha is the linear correlation, my T behave something like this. You can actually get this closed form. So if you know the distribution, you can get some sense of what is the behavior.
And I guess for the Y, Z here would not know 0, 1, but Z is really positive.
Right, yeah,
then it would be 1.
Yeah, exactly. Then it would be
marginal distribution.
Exactly.
So intuition-wise, the definition is basically the same as before, but now the function is the one where it has no sigma X before.
So here we have that this condition is for the joint space.
Okay.
But yeah, exactly. The intuition goes exactly the same. Yeah, it's just we have two levels of conditioning, and it would be messy to explain it. So.
I think that's time to wrap up. We can keep the discussion upstairs as usual. So let's send the speaker again.
Thank you.
Thank you, everyone. See you next week.